Welcome my dear learners for this course on design of machine elements 1. In this module 1 we were discussing on design for static strength. So far we have solved 7 numerical problems on design for static strength. Before moving ahead to discuss on stress concentration, I am interested to solve some previous VTU exam questions. And also I have given assignment in our lecture 6 where many students have commented to solve the assignment problem which I gave in lecture number 6. So let us discuss the same assignment problem, that is problem number 8 of our discussion on design for static strength. States that determine the normal stresses at the extreme fibers on the cross section AA of a C clamp loaded as shown in the figure 8. So this is the given figure. If you carefully observe, we have the section I section shown here in section AA, and we have load P 50 kN acting eccentrically to it. So this is an eccentrically loaded member, which means that the member is experiencing both direct stress as well as bending stress. So this you people already know from lecture 5 itself. Now applying the first principles, let us solve problem number 8. If I move for solution of problem number 8, let me redraw the section AA, which is an I section given for us. The I section is like this. So this is the I section what is given to us. And we know the dimensions, which is specified as 15 mm, 15 mm and 50 mm. This is 15, this is 50, and again this is 15. So this is the section AA, and this dimension is also equal to 15. Sorry, it is 50 millimeters, and this dimension is 15 mm. This dimension is also equal to 15 millimeters. So this is the section AA given for us, and it is loaded eccentrically here by load P, which is equal to 50 kilonewtons. Load P, which is equal to 50 kilonewtons. Now we know eccentricity. Eccentricity is nothing but distance of the load line from the centroidal axis. So if you carefully observe, the I section what he has given is symmetric about both x axis as well as y axis. If I fold, it is symmetric about the centroidal axis. If I fold here also, it is symmetric about the centroidal axis because the dimensions are symmetric. So therefore I should find the centroidal axis and measure eccentricity to find the bending stress. So since this is the eccentrically loaded problem, for eccentrically loaded problem for eccentrically loaded members, the maximum stress sigma max is given by sigma direct plus sigma bending. This you people already know. Now I want to determine the direct stress. So direct stress is known for us from the basics. Direct stress is given by force by area, which is equal to force acting is 50 kilonewton, 50 into 10 to the power of 3 divided by area. So to determine the area of this I section, we can take it as 3 rectangles. Rectangle number 1, rectangle number 2 and rectangle number 3. So therefore it is 3 times 50 into 15, 50 into 15 and again 50 into 15. So therefore we have 3 rectangles which are similar in dimension, 50 cross 15, 50 cross 15 and 15 cross 50. So it is 15 cross 50, 3 rectangles. So therefore the area will become 50 into 10 to the power of 3 divided by 3 times 15 cross 50. So the magnitude of direct stress is turning out to be 22.22 megapascals. 22.22 megapascals. All dimensions are in millimeters. Now to find bending stress, I should go for bending moment divided by section modulus. So therefore, if I go for bending stress, we know that bending stress is given by bending moment divided by section modulus Z, where section modulus Z is given by area moment of inertia divided by distance of the outer fiber from centroidal axis. Right. So now here to find the value of moment of inertia I can refer table 1.3a, page number 12 of our data handbook written by K. Mahadevan and Balavira Reddy. We are referring 4th edition. So according to our data handbook, if I refer table 1.3a of page number 12. If I refer page number 12, 1.3a of our reference design data handbook written by K. Mahadevan and K. Balavira Reddy, we are referring 4th edition, according to which for I section under consideration, he has specified the value of area moment of inertia I as capital B capital H cube minus small b small h cube divided by 12. Now comparing this sketch to the data handbook, it is found that the capital B is turning out to be 50, capital H is the overall depth, it is 50 plus 30, 5 plus 3 is 8, it is 80. And now coming to find small b, he has given this as b by 2 and this as b by 2. We know capital B is 50, b by 2 plus 15 plus b by 2 will be equal to 50. So compare the given sketch with I section given in table 1.3a. What I observed is that b by 2 plus b by 2 plus 15 is equal to capital B, that is 50. Hence if you solve, you will get the value of small b as 50 minus 15. Correct? It is b by 2 plus b by 2 is b. So therefore 50 minus 15 is 35. And this 50 is termed as small h. And small h is this one, which is 50. So we know all the values. So therefore I can find how much is the value of moment of inertia I. So hence moment of inertia I will become capital B is 50, overall depth is 80 cube minus small b is 35 into small h is 50 divided by 12. Hence area moment of inertia will become 50 into 80 cube minus 35 into 50 cube divided by 12. Let me put brackets properly. So if I solve, I will get the moment of inertia as 1768750 mm power 4. So this is the value of area moment of inertia for the I section given for us. Now where C is the distance of the outer fibers from centroidal axis, since this is symmetric sketch, this distance is nothing but half of 85. Correct? It is nothing but 25 plus 15. Here also it is 25 plus 15. The inner fiber distance from centroid will be 25 plus 15. that is 35. Whereas here it is 25 plus 15, that is 35. Put together overall depth is 80 millimeters. So therefore the value of C is nothing but h by 2, which is also specified in the same table 1.3a referring to page number 12. So which is nothing but h is 80 by 2, which is equal to 35 millimeters. So we know all the values, so therefore I can find how much is the bending stress. Sigma bending will be equal to bending moment. Bending moment for eccentrically loaded member is load into eccentricity, where eccentricity is nothing but distance from the centroidal axis to the load line or line of action of force. So this distance is what I should take. We have specified this distance as 150. So E is equal to 150 plus C. So this distance is C. This distance is C. So therefore E is 150 plus C. C is found to be 35. So eccentricity is 150 plus 35. So bending moment will be 50 into 10 to the power of 3 into eccentricity is 150 plus 35. This is the value of E. P into E divided by Z. Z is I by C, which is nothing but 1768750 divided by 35. So hence bending stress will be equal to 50 into 10 to the power of 3 into 150 plus 35. This is again multiplied by 35, that is h by 2. This is divided by 1768750, area moment of inertia. So bending stress will be equal to 183.04 megapascals. Now if you carefully observe, the bending stress and direct stress are tensile in inner fiber, whereas it is compressive in outer fiber. Both direct stress as well as bending stress is trying to open the C clamp, hence the inner fiber is subjected for tensile loading, whereas the outer fiber is subjected for compression because of bending. So therefore at inner fiber we have sigma is equal to sigma direct plus sigma bending, which is turning out to be 22.22 plus 183.04. It is 205.26 megapascals, whereas at outer fiber sigma is given by direct stress is causing tensile, whereas bending stress is causing compression. Hence it is 22.22 minus 183.04. Hence the answer will be 22.22 minus 183.04, which is equal to minus 160.82 megapascals. At inner fiber it is tensile, at outer fiber it is compression. So this is the solution for problem number 8, which is an assignment problem given in lecture number 6. Moving ahead, let us solve problem number 9, which states that the load F on C clamp shown in figure 9 is 37.5 kilonewtons. The clamp is made of cast steel with B is equal to 3H and eccentricity is 200 millimeters. If the allowable stress is 100 megapascal, determine the dimensions B and H. This problem is similar to the problem number 8. Only thing is that the cross section is rectangle here, whereas here it is I section. Let us solve this problem. If I move for solution of problem number 9, we have rectangular cross section given like this. Yes, specified this as breadth B and this as height H, and we have loading F whose magnitude is given as 37.5 kilonewtons, and the eccentricity is directly specified as 200 mm, and he has also given sigma allowable or sigma max is how much? 100 megapascals. It is 100 megapascals, and he has given a hint that B is equal to 3H. Find the value of B and H is the question to be answered. So this is also eccentrically loaded member. The maximum stress induced will be at inner fiber. So this clamp will be opening like this. So therefore inner fiber will be experiencing tensile because of bending stress, and outer fiber will be experiencing compression. So therefore let us solve for inner fiber, because inner fiber has the maximum stress, which we can observe from problem 8 also. So therefore sigma max, if I move for solution, we have sigma max is nothing but sigma direct plus sigma bending, which is happening in the inner fiber. Now let us solve one by one. This is at inner fiber. Now sigma direct is force by area. We have force F by area. F is 37.5 into 10 to the power of 3 newtons divided by area is B into H. Hence the direct stress will become 37.5 into 10 to the power of 3 divided by B is equal to 3H. If I substitute B is equal to 3H, it will become 3H square. So therefore further simplification will yields us the answer as 37.5 into 10 to the power of 3 divided by 3, which is equal to 12,500 by H square. Keep it as it is. Now if I go for bending stress, we have sigma bending is equal to bending moment MB divided by Z, where Z is nothing but area moment of inertia divided by distance of the outer fiber from centroidal axis. So this distance of the outer fiber from centroidal axis is C, and I want I. Now for rectangular cross section, we know that I is given by I is equal to BH cube by BH square by BH cube by 12. Now the careful observation will reveals that the depth is B, depth is not H. If you carefully observe, the depth of this section is B. And to confuse us, he has given the depth as B and width as H. Usually this is the depth. You can see, observe this sketch. The depth of this C clamp is this much. This is the depth of this C clamp. So therefore what we should take is for moment of inertia as HB cube by 12. HB cube by 12, because the actual formula is BD cube by 12, where D is the depth of the section. So here the depth of the section is replaced by B. So this is the depth of this section. Hence BD cube by 12 should be written as H into depth is b, so it become hb cube by 12. This is very very important. If you take it as bh cube by 12, you'll get the wrong answer, because depth of this C clamp is not h, depth of this C clamp is b. Now if I replace the given data and solve, I'll get the value of I as h into 3h whole cube by 12. So therefore the value of I will be 3 cube by 12, which is 2.25 h to the power of 4. Kindly make a note. The formula for area moment of inertia for a rectangle is BD cube by 12, where D is the depth, B is the breadth. Here the depth of this section is B. So therefore the formula for area moment of inertia will become HB cube by 12. So we have got moment of inertia as 2.25 h to the power of 4. Now C is the distance of the outer fiber from centroidal axis. So this distance is nothing but b by 2. Distance of the outer fiber from the centroidal axis is b by 2. B is 3h, so it will be 3h by 2. So now bending stress will become, sigma bending will be MB. MB is 37.5 into 200 is the eccentricity into 10 to the power of 3, because load is 37.5 kilonewtons, divided by Z. Z is I by C, which will be 2.25 h to the power of 4 divided by 3h by 2. 3h by 2. So if I simplify, sigma V will become 37.5 into 10 to the power of 3 times 200 is the bending moment. This is multiplied by 3 divided by 2 into 2.25. 2 into 2.25, which is turning out to be sigma B is equal to 5 into 10 to the power of 6, 5 into 10 to the power of 6 divided by h cube. 5 into 10 to the power of 6 divided by h cube. Right. So now we know the value of sigma max, which is nothing but sigma allowable, which is 100. So therefore, using equation 1, from equation 1, sigma max is 100. 100 should be equal to sigma direct is 12500 divided by h square plus 5 into 10 to the power of 6 divided by h cube. So since we have cubic equation, if I simplify, I will get the solution as 100 h cube or throughout I will divide by 100, it will become h cube minus 12,500 by 100, it will be 125. H is the remaining, minus, if I divide this by 100, I'll get it as 5 into 10 to the power of 4. This is equal to 0. So this is the equation I will get. What I done here is I threw divided by 100 and took h cube as LCM and took it to right hand side and rearranged the equation. I got this equation, that is h cube minus 125h minus 5 into 10 to the power of 4 is equal to 0. Now if I solve using equation mode, taking the cubic equation, coefficient of h cube is 1, coefficient of h square is 0, coefficient of h is minus 125 and constant is minus 5 into 10 to the power of 4. So the value of h is turning out to be 37.97 mm. So other two answers are imaginary. So remaining totally we will get 3 roots. I am getting one answer as 37.97 and remaining 2 roots are imaginary. So therefore we can neglect remaining 2 roots and adopt the real value, that is 37.97 mm. So hence I can take h as 38 millimeters and b is equal to 3h. It is 38 into 3, which is 114 millimeters. So the solution for this problem is h is equal to 38 mm and b is equal to 3h, which is 114 millimeters. So this is how we should solve the problems on C clamp, which I have also explained in our lecture 6 and solved the assignment problems here. In our next lecture I will take up a special case problem on design for static strength, and later we can begin our discussion on stress concentration. That's all from this lecture. Thank you all.